vectors. And there's lots that we've done. Yes, a squared plus b squared equals c squared. Someone's writing c squared minus a squared equals b squared. Yes. Yes, someone's putting Toa. Good stuff. Nice. Oh, yes. It doesn't matter how you get from A to B as long as you get there. Yes. Vectors. Love it. Half A times B times SX. Yes, a correctly labeled triangle where the angles are marked with capital letters and the lowercase letters are side lengths, and in particular, the lowercase letters are opposite their capital counterpart. Ooh, yes, tan equals sine over cos. Absolutely. Absolutely, that's true. Top number equals left or right. Bottom number equals up or down. Yes. Negative left, down, positive right and up for vectors. Absolutely. Yep. When you're looking at column vectors, indeed. Oh, yeah, there's another page, isn't there? People might be on different pages doing different things. A squared equals b squared plus c squared, take away 2bc cos. Yes. I'm loving this. Oh, I've only got 17 students on the Google Classroom, so not everyone's going to get this notification necessarily. Anyway, I'll come back to... Ooh, lovely. Yep, so someone specified that that's the cosine rule for finding a side. In trig graphs, sine and cos are continuous lines while tan are separate lines. Yes, there are points of discontinuity with tan, absolutely. Indeed. Is there anyone who knows how to draw any of the graphs? Maybe on the next page. And does anyone know what the sine rule is? Question mark, question mark. Yes. To the person who's writing that. Yes, sine A over A equals sine B over B equals sine C over C. Indeed, this is great. Someone's put a half A plus B equals sine C. What formula is this on the second page? Or maybe there's a error with the formula that you meant, perhaps?
Is it to do with triangles?
It is to do with triangles. I think the thing that the person was going for was, what do you call it? The area of a triangle, but they might have got it a little bit incorrect.
No,
Maybe
it's supposed to say sine of x.
What's that?
It's supposed to say sine of x. I swear that's how you do it.
No, not sine of x. Sine of c is there, indeed, but we might just need to retweak that formula.
The area of a triangle, right?
Area of a triangle, yeah. Ooh, someone's drawn a tan graph. This is good. Can somebody else maybe add in some numbers for that tan graph? Where does it cross the x-axis? Where's that first asymptote? What numbers are we dealing with? Or just like a tan graph that's been shifted, should I say? Ah, yes, working out exact angles. Someone's put the hand. Yep. Someone's put the sine graph. Someone's put the sine graph on the left and the cos graph on the right. The horizontal line can definitely be useful when you're working out things like sine of x equals 30. What are the different values? 100%. Whoever's trying to draw the tan graph, I'm guessing, you're trying to get it to go exactly through the origin. It's good. Lovely tan graph. Nice. Yeah. Well, the recall there is really good. Okay, let's go into some actual questions that we can ask ourselves. So on slide 3, I'm just going to write down some questions. So I've got a right angle triangle that's isosceles. Can we fill in as much information as we can without the use of a calculator? And parallel to that, I'm going to put another triangle. This one's an equilateral triangle. So all 3 sides are the same length. But I'm also going to, so this is a equilateral, and I'm going to split it down the middle. Like that. And this side length is 2, and this side length is 2. And it's the big black triangle is equilateral. Can we work out as much information as we can there? And then on the next slide, I'm going to put a triangle. And I'm going to, it's another right angle triangle. One side length is x, one side length is y. Can we work out an expression for the hypotenuse? Work out an expression for the hypotenuse. Ooh, someone's really going for it with that slide 5. Is everybody on the Jamboard, by the way? I don't think everyone is. Nice, yes, that's a great expression for the hypotenuse. Now, can we work out an expression for sine theta? Can we work out an expression for cos theta? And for tan theta? And for sine theta squared plus cos theta squared? This is like pushing people now. An expression for all of those things. So there's quite a lot going on this Jamboard. Ooh, lovely. I'm loving this. 30 degrees, 60 degrees, 2, yes. The 1, 1, the root 2, yes. Loving that, the 45 degrees. So back on slide 3, I'm going to add, can we work out an expression for sine of 45 without a calculator, of course, an expression for cos of 45, and an expression for tan of 45. With this, on slide 4, someone's put the length 4 at the bottom. If the black triangle is equilateral and 2 of the black lengths are 2, then the bottom length can't possibly be 4. There's only one possible length it could be, given that the whole black triangle was equilateral. Ooh, yes, okay. So for sine of theta, x over the square root of x squared plus y squared indeed. Cos of theta, cos of theta isn't quite y over x. Whoever wrote cos of theta is y over x. And tan of theta isn't quite y over x squared plus y squared. On the next slide, to make it just a little bit more dynamic, we've got what is sine of 90 minus theta, the same thing as, and what is cos of 90 minus theta, the same thing as. So there's quite a few tasks. And of course, you're more than welcome to ask if you need help. And just to help you with this question, theta is over here. I've got a right angle. So how does 90 minus theta fit in this triangle? how might we be able to extend to determine what sine of 90 minus theta is? Oh, yes, someone's put an expression for sine theta squared plus cos theta squared, or sine squared theta plus cos squared theta. Now, what does that actually become the same thing as? Oh, and also, wait, somebody's put x squared over x plus y. I think you missed the squared, so I'll just put that in for you. Squared, 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 and squared.
Sir, please can you explain slide 5?
Slide 5?
Yeah.
Yes, of course. So which bit do you need explained?
All of it.
Right, so I've put a right angle triangle and I've called one side length x and another side length y. So someone's concluded that by using Pythagoras Theorem, the hypotenuse is going to be the square root of x squared plus y squared, because x squared plus y squared equals the hypotenuse squared, right?
Yeah, no, I got that bit. Just the bits after that.
So sine of theta, remembering our relationships with sine of theta, cos of theta, tan of theta, sine is opposite over hypotenuse. So the opposite to the theta is x. The hypotenuse is the square root of x squared plus y squared. There is a mistake though with cos of theta. Somebody's corrected the tan of theta, opposite over adjacent. But to the person that asked, what do you think now cos of theta would have to be if I rub it out?
Y over square root of x squared plus y squared.
Perfect, yeah, because it's adjacent over hypotenuse.
Yeah.
So y over the square root of x squared plus y squared. And to the person that wrote that sine of theta squared plus cos of squared theta is x squared plus y squared over x squared plus y squared, what's that the same thing as?
Oh, so I was going to ask, is it just one?
Yeah,
Okay.
yes, we got it. Yeah. It's the same thing as just one. So in actual fact, you've now just established an identity there. So someone wrote before that tan is the same thing as sine over cos. So on slide number 7, I can write tan of theta is identical to sine of theta over cos of theta. But equally, I can also write that sine squared theta is the same thing as sine theta all squared, plus cos squared theta is identical to 1. These are two identities that actually, that are ones that are a thing, 100% a thing. So we can play around with these identities to just prove results. So for example, hold on, just give me a moment. Ooh. But I did want to go back to some of the other questions as well. So this video link will show you how you can play around with some of those identities that we just came up with. I've sent it in the chat. And to the person that's writing sine of 90 minus theta, there's actually an easier way to think about this. And my question is, what is the third angle in the triangle? What is an expression for the third angle in the triangle, should I say? That's on slide number 6, if anyone's having a think about that. Ooh, okay, right. So, lovely. On the slide 4, we've got the equilateral triangle, and we've got a side length of 2, side length of 2, 1, 1. Square root of 5, how was that calculated? for anyone that was working on slide 4? If anyone cares to explain, or maybe suggest something alternative.
Would it not be 3?
Why is that?
Because it's 2 squared, take away 1 squared.
Indeed, yes. So because we're working out a shorter side, not the hypotenuse, we've got to do subtract. So it would be the square root of 3. Indeed. And with that triangle now, can we use that triangle to determine the value of sine 30, the value of cos 30, the value of tan 30, the value of sine 60, the value of cos 60, and the value of tan 60. Oops. And are there any questions that people have so far? Because there are lots of things that are going on, so it's perfectly okay to have questions. And on slide 3, someone's written that sine of 45 is the square root of 3 over 2. In what sense have we used a triangle to deduce that? That's a question there to think about. Lovely. So sine 30, in fact, I should put the equal signs. And then there's like a challenging question on slide 7, if anyone wants to have a think about that. Show that cos to the 4th theta minus sine to the 4th theta is identical to cos squared theta minus sine squared theta. So we need a convincing explanation as to how that works. So for example, Sam, if you're there, that might be a problem that you might want to assess. Okay, so just verifying some of the other. Oh, okay, someone's got all of them on slide 4. So sine 30 is so opposite over hypotenuse. So the 1 is opposite, the 2 is the hypotenuse. Yes. Cos 30. Cos 30 is not quite right. And tan 30 is also not quite right. I think it's the same person that wrote the expressions for cos and tan in the other triangle incorrectly, because it's the same kind of mistake-ish. But it's okay. So just remember what cos is and what tan is. Looking at the sine 60, 60 opposite the 60 is root 3, and then the hypotenuse is 2, so root 3 over 2. Cos 60 is adjacent over hypotenuse, so 1/2, and tan of 30 is tan of 60 is root 3 over 1, which is just root 3. Indeed. And yes, cos of 30 indeed is opposite over is adjacent over hypotenuse, and adjacent to the 30 is root 3, yep. So root 3 over 2. And then the home run, tan of 30 is opposite over adjacent, 1 over root 3. Lovely stuff. Lovely stuff. So slide 4, I think, is we've accomplished what we needed to do on slide 4. So it remains that we need to work out slide 3, the values of sine 45, cos 45, tan 45, using that triangle. Slide 5, I think we've accomplished as well. We've worked out that sine squared theta plus cos squared theta is 1. Slide 6 is still a bit of a mystery, and slide 7 is also a bit of a mystery. In fact, I might even add just a little bit more dynamics to this. Sine theta plus cos theta all squared plus sine theta minus cos theta all squared is identical, is equal to a number. What number? Okay, so someone's put cos 45 as 1 over root 2. So 45, and you've got the adjacent over the hypotenuse. Equally, you could have used this 45 and this adjacent over the hypotenuse. Comes out to be the same. Tan 45, yes, 1 over 1, because the opposite and adjacent are both 1. But sine 45 is still not quite right. And also slide 6. A good idea would be to work out the third angle in this triangle. That's something that I would say. And for slide 7, I think the second question might actually be more approachable in the sense that there are more things you can try to do straight away. Whereas with the first one, it's a bit like if you're not thinking about this kind of thing, then it could be quite tough to spot. But let me give some hints. So for slide 7, some hints might be, I'm going to send the hint in the chat. I know it's been a while since we've done maybe these kinds of things.
Sorry. For the one which is like sine theta plus cosine theta, all of that squared, plus sine theta minus cosine theta, all of that squared.
Mm-hmm.
Would it? Oh, sorry. No, I've done something wrong here. Let me.
Okay.
Well, would it just be actually? Yeah. Wait. Would it be? Can I say or?
Yeah, you can say.
Is it 2 sine squared theta plus 2 cosine squared theta? Because where do you go from there?
Where do you go? Wait, as in that's what you've simplified it to?
Yeah.
Okay, let's go for it. So what did you get when you expanded the first one?
Would that just end up being 2? I got sine squared theta plus cosine squared theta plus 2 cosine theta sine theta.
So sine squared theta plus cos squared theta plus 2 sine theta cos theta.
And then for the second bracket, I got plus sine theta squared. Sorry, sine squared theta plus cosine squared theta minus 2 cos theta sine theta.
Yeah. Indeed.
So then those two cancel out. They're like
Yep. The 2 sine this and this will cancel. Yep. Because of the minus.
And then you can add these things. So then you get 2 sine squared theta plus 2 cosine squared theta. And
yep.
And because sine squared theta plus cosine squared theta is 1, does that mean that this is going to be 2?
Indeed, yeah. Because this is the same thing as 2 open bracket sine squared theta plus cos squared theta. Or we could have just established that each pair of sine squared thetas plus cos squared thetas were 1 each. But yeah.
Okay, cool.
Absolutely. So yeah, it comes out to 2. Nice. Yes. This is good. Now the other question is, what about that one on top? How would we like show that cos to the 4 theta minus sine to the 4 theta is the same thing as cos squared theta minus sine squared theta?
I can.
What's that?
Is it? Well, I don't. I can
Yeah.
wait. But
You're more than welcome to share your thoughts.
Because sine squared theta plus cosine squared theta is just 1.
Mm-hmm.
Multiplying anything by 1 isn't going to change it.
Mm-hmm.
So if you times sine squared theta plus cosine squared theta by sine squared theta plus cosine squared theta,
Mm-hmm.
is that going to come out with cosine to the 4 theta minus sine to the 4 theta?
Indeed, indeed, indeed. So yeah, if we take this first expression, and yeah, we times it by 1, but our special expression for 1 is going to be this. Then yeah, this is what we call the difference of two squares. And that becomes cos to the 4 theta minus sine to the 4 theta, yeah. Nice. Nice, nice, nice. Well, here's another thing then for you to think about. So we've got the expressions sine of theta over cos of theta is identical to tan of theta. And we've got the sine squared theta plus cos squared theta is identical to 1. I should probably duplicate this slide. Oh dear. How do I duplicate? Yes. Okay, so I'm on slide 8. Here's one question. If sine theta is equal to x, then what is cos of theta in terms of x? Oh dear, that is not how you spell terms. In terms of x. And what is tan of theta in terms of x? And the clue there is using those identities. For everyone else as well, I've actually got together a quiz. If you guys remember quizzes, when we did it in the last lockdown. I think just a better way to do it would be like this. Oh no. Yeah. So if we go on quizzes, I think I sent something to Google Classroom, but I don't know if you guys can see it. But if you can't see it, no worries. What I will do is on slide number 9, I've put like the joining info. Should be appearing now. And it's just a little quiz on just basic trig. Just see what people know. Yay, people are on it. Well, one person's on it. But whilst people are waiting to join, there are, of course, the other questions that we can think about. And I realize as well that I haven't actually looked fully at... okay. Now we've got somewhere. Someone's worked out that the third angle is 90 minus theta, and in which case sine of 90 minus theta is y over x squared plus y squared. Here's a question though. For the person that wrote that on slide number 6, what's another expression for y over x squared plus y squared? Using that triangle, what's another expression for y over x squared plus y squared? And equally, for using that triangle, what's another expression for x over x, the square root of x squared plus y squared? I meant to say square root each time. What's another expression for those things using that triangle? So again, lots of different things to be looking at. So we've got 4 people on the quiz. But again, whilst we're waiting for more people to enter, we also have the question on slide 6 to think about. What's another expression for y over the square root of x squared plus y squared? What's another expression for x over the square root of x squared plus y squared? And slide 8. If sine theta equals x, what is cos theta in terms of x, and what is tan theta in terms of x, using the identities above, using the relationships that we know to be true to normal mode. We've actually covered quite a few things. I do want to finish the one for slide 8, but just to recap what we've done. So we first of all just wrote out formulae that we know for trigonometry. So we wrote Pythagoras Theorem, cosine rule, sine rule, the graphs of tan, sine, and cos, the hand for the different values that we need to know, and also we looked at slide 3. Slide 3 still needs fixing. The value of sine 45. And also slide 4. We've got, that was complete. That was mission accomplished. Slide 5 was nice. We accomplished that as well. Slide 6. Okay. With slide 6, the idea is using this triangle. I think I see what this person's done. You've multiplied top and bottom by the square root of x squared plus y squared. That works. But the actual thing that I was looking for was simply that this is the same thing as cos theta. Cos theta also has the expression y over the square root of x squared plus y squared. And equally with this one, cos of 90 minus theta is the same thing as sine of theta. Going on slide 7, we worked out that was 2. We proved that cos to the 4 minus theta minus sine to the 4 minus theta is the same thing as cos squared theta minus sine squared theta. And then on slide 8, I don't know if anyone had any ideas or if they wanted me to explain. Any ideas at all? Okay, for slide 8 of the Jamboard, if we had that sine of theta is equal to x, and we know that sine squared theta plus cos squared theta is 1, then replacing sine squared theta with x squared, we get x squared plus cos squared theta equals 1. So therefore, cos squared of theta is equal to 1 minus x squared, and then cos of theta must equal the square root of 1 minus x squared. So that's that relationship there. And then, now that we know sine and cos, we know that tan of theta is the same thing as sine theta over cos theta. So that gives us x over the square root of 1 minus x squared. And that's an expression there in terms of x. Just to leave you with a nice problem to finish with, and for anyone who's interested. So using also the facts that sine of 90 minus theta is identical to cos of theta and vice versa, how might we go about evaluating this? Sine squared of 0 plus sine squared of 1 plus sine squared of 2, still in the lesson, 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 still in the lesson. That's why sine squared of 2 plus sine squared of 3 plus dot 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 plus sine squared of 87 plus sine squared of 88 plus sine squared of 89 plus sine squared of 90. So it's basically adding up all the terms from sine of 0 to sine of 90. What might that be? And why? That's like a really long question to think about, but there we go. Are there any last questions before we finish up.
So what topic is this? Like, what would it come under?
I mean, this is trigonometry, but I've like, if you haven't noticed already, I've pushed you like well beyond GCSE.
Okay, yeah, because I was wondering if it was going to come up in the exam.
No, this would not come up in your GCSE exam. Matthias, you raised your hand.
So I don't have a calculator. How am I meant to do this?
You don't actually need a calculator to do this, believe it or not. Like you definitely wouldn't go about putting all of these values in your calculator, because that's 91 different values to put in your calculator. Your calculator wouldn't fit all of it.
Fair enough.
So the approach definitely would not be to think about putting it all in your calculator or even evaluating everything, but it's about using the relationships above.
Cool.
Yes. I think this is definitely one where you want to collaborate with other people if you want to have a solution for this. This is quite a interesting and tough problem. It's not supposed to be easy. And it's not supposed to be something that you just come up with in, 30 seconds necessarily.